Second half of section 310, page 209, we're looking at differentials. There are not many times that I have to supplement your textbook. I think maybe just a few times all year long. But this is one of those times that I really wanted you to have more information about differentials than the whole 2 paragraphs that they give us on page 209 before they jump into a pretty elaborate one example. So I made you some copies that are there in your notes packet. So you've got your front page that is your note sheet for today, but then behind that you have several pages copied out of another textbook. And so that's what you see here on the screen is just what's there in that book. So previously we have talked about Leibniz notation, that dy dx notation that we use for derivative, and we were careful to say this is just a singular notation. It's not like a fraction, it can't be broken apart. But Leibniz himself, when he was studying this, regarded the dx and the dy as being 2 separate quantities. He thought of them as infinitesimals. That is, quantities that, although they're not zero, they're smaller in magnitude than any finite quantity. So just this itty bitty, teeny weeny, infinitesimally small quantity, like as close to zero as you can get. And so he imagined that in the limit, change in x and change in y somehow become infinitesimal quantities, dx and dy respectively, so that that difference quotient, change in y over change in x, becomes the derivative dy over dx. Now, Leibniz' point of view has persisted with some mathematicians and most engineers and scientists, and they do prefer to think of dx and dy as those infinitesimal quantities. Whether you agree with that or not, which we would need a whole lot more information and higher levels of knowledge to make a decision like that, part of Leibniz' concept can still be salvaged by regarding dy and dx as literally being a fraction. 2 separate pieces, a numerator and a denominator, a ratio, if not of infinitesimals, then of the differentials dy and dx. And so that's what we want to look at today, is the idea of a differential, where we're thinking of that derivative as a fraction that can be separated into 2 separate differential pieces. If that's the case, then when I say the derivative is equal to dy over dx, I could break that apart into 2 separate pieces, multiply both sides by that denominator of dx, and I would get the definition of a differential, that dy is equal to the derivative times dx. And so that's the notation that we're going to use for a differential. That's the definition that they give us there in that handout. We don't really have like a box and a definition in our book. It is a bold print term there on 209 that they tell me that if the derivative is equal to dy over dx, if you multiplied both sides of that by that denominator dx, you would get dy is equal to the derivative times dx. And so that's our definition of the differential. So let's catch a couple of examples. We didn't have very many examples in our textbook. So here are a few extras that are also coming from that handout in your notes packet. And so example number 1 that they give us there, they say if f of x is equal to this quadratic, find dy. All right, so to find dy, I need the derivative, right? So what's my derivative? 6x minus 2, right. So I can say dy over dx is equal to 6x minus 2. So how do I get dy by itself? Multiply both sides by dx. And so my differential dy would be 6x minus 2 times dx. And that's it. That's my differential. Now sometimes I can give an equation for the differential. Other times I can actually go ahead and find a value for the differential. And so that's the second example that we have here. They said, okay, using that same equation, if we told you the value for x and the value for dx, then you'd be able to plug in the value for x and plug in the value for dx and actually come up with a number for dy, right? So let's do that. Let's take that same equation for the differential we just had, and let's put 1 in the place of x, and let's put 0.002 in the place of dx. So 1 in the place of x, 0.002 in the place of dx. All right, so what are you going to get for dy? Yes, 0.008. So that would be my differential dy. So again, for the differential, sometimes you can come up with an equation, sometimes you can come up with a value. And the little red numbers that you see over here are the homework problems that are going to coincide with that type of an example. So 15 through 20 are like that first type, and 21 through 26 are like that second type. All right, so that leads us to our textbook on page 209. And they go through and they talk there not just about the algebraic definition of a differential, but they also go back to the definition of derivative, how we thought of it as the slope of a tangent line, and how we had the two different values that were approaching each other so that the limit between them was getting closer and closer to zero. They kind of go through here and do a geometric discussion of a differential to help you see that. So as you read through that, that might give you just a different take on the idea of a differential. So they tell me that I can compare the derivative with the differential in several ways. All right, we've been talking about the derivative is change in y over change in x, and the differential, if you think of the derivative in Leibniz notation as being dy over dx, in that case, it's like the change in x parallels with dx, and the change in y parallels with dy. And so they tell me here on page 209 that your change in y will be an approximation of your differential dy if two things are true. If dx is equal to the change in x, and if the change in x is small. All right, well, let's go back and let's think about what the change in y is. Change in y is just y2 minus y1, right? It's the numerator in the slope formula. If you want to find the change in y, typically you have to say f of x sub 2 minus f of x sub 1, where we plug in the two x values to find the y values and subtract them. That means that if I'm starting at one x value and changing my x to get to a second x value, I could also think of this as the starting value plus the change in x to get to my second x value, that f of x sub 2, minus my starting x value, f of x sub 1. So they've gone through here and just defined it for us in several different ways to help it click for us. So for example number 4, if we think, as they told us, that change in y is a good approximation for dy, they want us to see that. So in example 4, it says compare the values of change in y and dy using this cubic equation and using the values as x changes from 2 to 2.05. And then we're going to redo this problem as x changes from 2 to 2.01. Why? Well, because they had mentioned to us that this is a good approximation if the change in x is small. So what we want to see is that, okay, here the change in x is relatively small, and we're going to get a good approximation, but here where the change in x is even smaller, we're going to get an even better approximation. Okay? So for the first one, if I want to find change in y, that's just f of x sub 2 minus f of x sub 1. All right, so here's my starting point, x sub 1. Here's my stopping point, x sub 2. So I could go through then and say if I want to find the change in y, y2 minus y1, I just want f of x sub 2 minus f of x sub 1. So again, this was my starting point of 2, my stopping point of 2.05. X sub 1, x sub 2. So we're just going to plug in f of x sub 2 minus f of x sub 1. Now, obviously, when I take 2.05 and I plug it into that function, I'm using my calculator, because 2.05 times 2.05 times 2.05 is not something they're going to ask me to do by hand. So we're going to do 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. So when we throw that into our calculator, we're going to get 9.717625. Now, we could plug the 2 in with no problem without a calculator. So if we plug into 2 cubed is 8 plus 4 minus 8 plus 1 is just going to give us 9. So when we subtract those values, our change in y is 0.717625. So nothing new about that for us. We've, done that since Algebra 1 when we were calculating slope and finding change in y values. The dy is what's new for us today. So if I wanted to find dy, what do I need first? The derivative, right. So what's my derivative going to be? All right, 3x squared plus 2x minus 2. And if I just want the differential dy, then we're going to take that derivative that we just found and multiply it by dx. So doing exactly what we were doing in the previous example, since we have an x value of 2 and a change in x value of 0.05, we can plug in 2 for x and 0.05 for dx and actually be able to come up with a numerical value for dy. And you'll notice that sure enough, dy is a really good approximation for the change in y. I mean, it's only off by 17 thousandths, right? That's pretty good. But what would make it even better is that if that change in x is small, so I get a better approximation the smaller it gets. So this time let's go back and approximate where change in x is a smaller value, 0.01. And again, that same idea of how when we found the definition of derivative, we used the slopes of the secant line, and we let the distance in between those 2 points get smaller and smaller and smaller. The change in x approached 0 to give us a better approximation. Okay, so same kind of idea here. We want our change in x to get smaller and smaller and smaller to give us a better approximation. So we'll start the same way. We're going to come down here and find the change in y, only this time we're going from 2 to 2.01. So we're going to do f of 2.01 minus f of 2. The f of 2 we did just a second ago and had gotten 9. F of 2.01 we're going to want to throw in our calculator. So 2.01 cubed plus 2.01 squared minus 2 times 2.01 plus 1 is where we're getting our 9.140701. So we can subtract, and there's our differential. All right, then let's find dy. So dy is still going to be the derivative times dx. We're still going to plug in that same value of 2 for x. So really the only thing that's going to change is that we're using the change in x of 0.01 instead of 0.05. So on that second part, everything stays the same, you'll notice, except for we just replace 0.05 with 0.01. And now look at the comparison of dy with change in y. We're only off by 7 ten-thousandths. So that's a fantastic approximation. So the moral of the story, the point of that whole example, is over on the top of page 210. It says, notice that the approximation change in y for dy becomes better as the change in x becomes smaller in example 2. Notice also that dy was easier to compute than the change in y. So for more complicated functions, it may be impossible to compute the change in y exactly. In such cases, the approximation by differentials is especially useful. So anytime in calculus I have 2 different ways of coming up with the same thing, I want to know that, because there are going to be some things that I come to that maybe finding the change in y would be much more difficult than finding dy. And other times maybe dy would be more difficult than finding the change in y. But you can see that when that change in x is a small value, that I could use either one of those things to get a good approximation of what that value would be. All right, so the last problems that we were doing here are going to be like, that last example going to be like 27 through 30 for the homework tonight. So on our homework, we're working on pages 211 to 212. 211 to 212.